Hello everyone, let us start lecture 19. Today we will finish our discussion on ΔHmix and its equation relating bond energy and concentration. In our last lecture, we have seen that ΔHmix is nothing but ΔHmix, since we have considered ΔHmix equal to 0. This is the assumption which is considered while constructing quasi-chemical model, and then it becomes PAB, which is the number of AB bonds in a binary solution of A and B with this energy contribution Now, we have to find out the value of PAB, this evaluation we have to do as a function of concentration of A and B in the mixture. Now, if we have some lattice and that lattice is formed by A and B atoms, then the probability of finding A atom at any site is equal to Xa, which is the mole fraction or the atom fraction. Now, the probability of finding another A atom just next to the A atom is nothing but Xa into Xa. So, that means this indicating AA bond type, or other way the probability of formation of AA bond. And remember, here Xa is equal to Na by N0, since we have considered in the beginning that Na number of A atom and Nb number of B atom are joined together or mixed together, and that time this combination of these two gives us Avogadro number of atoms. That means we are forming 1 mole of mixture or solution. Similarly, same way the probability of finding another B atom just next to another B atom, which is nothing but the probability of finding BB bond is nothing but XB into XB, which is XB square, and this also leads to Xa square. So, now we see that if in a mixture we have A and B type of atoms, then what is the probability of finding AA bond type or BB bond type, which is proportional to XA square as well as XB square. Now, we have to find out that what is the probability of finding A atom next to a B atom or finding B atom next to a atom. That would lead to the concept of probability of finding AB type of bond. So, now probability of finding B atom next to A atom is nothing but, first is the probability of finding A atom at any site, which is XA, and then the next site would be occupied by B atom, so XB. If we try to find out AB bond with reference to A atom, because here we are trying to find out AB bond with reference to A atom, we will also see the possibility of AB bond formation with reference to B atom. So, that means probability of finding A atom next to B atom would be, first is the probability of finding B atom at any site is XB, and then next would be the probability of finding A atom next to it. So, hence probability of AB bond formation would be proportional to XA XB 2. So, that means this 2 is coming, because one case we are finding it AB bond formation probability with reference to A atom, and in the second case we are finding AB bond formation with reference to B atom. Now, if I try to see a pure case, pure A lattice, so that time we know that PAA, that is number of AA type of bond in case of pure substance, is nothing but Na Z by 2. I can write it in this fashion, Na by N0 into Z half. So, it is nothing but N0 into Z into XA. Now, this is the number of AA type bond in pure case, but once we consider a mixed situation, that means we have A type of atom as well as B type of atom, both are present in the crystal, which is formed after mixing A atom as well as B atom. So, that case, in case of mixture or solution, initially if I consider the solution formation, that time I will have this concept valid. Z. Now, if I try to find out PA in the mixed condition, that time I have to just multiply this factor with or this factor with XA, because I am trying to find out position of A next to another A atom. So, it would be half Na N0 or N0 Z XA into XA is equal to half N0 Z XA square. I can also find out BB in mixed condition is equal to half N0 Z x b square. Now, if I try to find out P A B bond in mixed condition, would be equal to 2 P A A plus P A B equal to N A Z equal to N 0 Z N A by N 0 N 0 Z X A. I have already found out the value of P A A in the mixed condition, which is this one. So, I just replace that value half N 0 Z X A square plus P A B equal to N 0 Z X A. Remember, this Z is coordination number. So, now we can get P A B equal to N 0 Z into 2, because here we have to consider this 2 factor. So, N 0 Z X A minus N 0 Z X A square. So, then becomes N 0 Z X A 1 minus X A. We already know that X A plus X B equal to 1, hence X B equal to 1 minus X A. So, if I replace that, P A B equal to N 0 Z X A X B. Now, I know that del H mix equal to P A B E A B minus by 2. So, then I just put the value of P A B as a function of coordination number, mole fraction of A and B in the mixture. So, then N 0 Z X A X B E A B minus E A A plus E B B by 2. So, this is my final del H mix expression. Since this one we have considered as energy E, so then I can write del H mix E X A X B. This particular term is written as omega. So, I can write it as X A X B omega. So, the final expression in terms of omega, it becomes X A X B this. This is my final expression. Now, we started with ideal solution where del H mix was considered as 0. Now, this was my initial expression when we tried to consider solution formation. So, this can be written as X A G A 0 plus X B G B 0 plus del H mix minus T del S mix. During in case of ideal solution, this is 0, but since we are considering non-ideal case where del H mix can have positive or negative value depending on the value of this quantity, it can be positive or it can be negative. So, then we have to consider this del H mix value in our calculation of G2 or the free energy of mixed solution phase. It can be liquid, it can be solid. So, this particular G2, as we have understood that this is indicating free energy of a particular phase in the mixed condition or solution condition. Now, we can do little bit of adjustment here, x a G a 0 plus x b G b 0. See, this 0 superscript 0 is indicating the standard value, and every time this is indicating a particular phase when that pure metal is in that particular phase. Let us say if it is a solid. So, both the standard values are indicative of pure solid A and pure solid B at 1 atmosphere pressure, at of course, at the temperature where we are considering that solution formation, plus x a x b minus T. Now, I can replace this ΔHmix expression x a ln x a plus x b ln x b, then Z 2 equal to x a G a 0 plus x b Z b 0 plus I can write this one as x a plus x b. Now, this is nothing but 1. So, I can just make a mention of this plus R T x a ln x a plus x b ln x b. G 2 would be equal to x a G a 0 plus x a x b square plus x a ln x a plus G x b G b 0 plus x b x a square plus R T x b ln x b. I just redistribute the entire expression. So, I can write G 2 equal to x a G a 0 plus x b plus, sorry, I just missed one R T term here, R T ln x a plus x b G b 0 plus x a square plus R T ln x b. Then I can write it as x a 1 minus x a, if I convert everything in terms of x a, because one side would be all x a and another side would be all x b, plus R T ln x a plus x b G b 0 plus 1 minus x b square plus R T ln x b. Now, this entire term can be written in the form of chemical potential, which is the chemical potential of A, and this one is nothing but chemical potential of B in that particular phase. So, G 2 equal to x a mu A plus x b mu B. This is in case of non-ideal solution. Now, here the only difference, if I try to find out the expression for G 2 in case of ideal situation, G 2 equal to x a mu A plus x b mu B, I simply put I d. in case of ideal solution, that time the only extra part is this quantity, or in this case it is this quantity. So, the difference between chemical potential in case of non ideal solution and chemical potential of that particular element or component in that solution in case of ideal case, the difference is in case of mu A and 1 minus x b square in case of mu b, this is the difference. Mu A and mu B with mu A ideal and mu B ideal. And just to mention, mu A ideal is equal to G A 0 plus R T ln x A, and mu B ideal is equal to G B 0 plus R T ln x B. So, this has been shown in previous lectures. So, the final expression for in case of non ideal situation is nothing but x A mu A plus x B mu B. This is the expression for non ideal situation. At any concentration, if I try to find out the free energy of the mixture, we have to just put a tangent at that particular composition on that free energy line G2 line and see their intersection point on two pure metal side. So, for example, if I try to see this particular free energy composition diagram, let us say if this is G, this is x b, and in case of non ideal situation, if my free energy line is this is G2, let us say some phase, this P means phase. So, then let us say if I try to find out at x 0 what would be my chemical potential in case of non ideal situation, I just need to draw a tangent on that particular point over that free energy line, and this would be my mu b and this would be my mu a of that phase. So, it is exactly the similar trend, but only thing is our free energy calculation needs to take care of ΔHmix or this omega term. Now, we have seen a situation, one situation we have already seen, which is ΔHmix is equal to 0. And accordingly, we have done all sort of calculations in order to find out phase diagram, because that time to solve that mixture, those particular situations was little easy, because we did not have to consider ΔHmix. And for example, in this case, which is absolute ideal situation, ideal solution, and we have drawn an isomorphous phase diagram. And in that case, we have taken a solid liquid isomorphous situation. But if it is non-zero value, then situation would be little complicated. Let us consider a situation where ΔHmix is equal to is greater than 0. When we are considering greater than 0, it can have two more situations. One is ΔHmix greater than 0 or greater than 0. So, these two situations can arise. But simply if we try to consider if it is greater than 0, what would be its effect on the free energy line of the solution of a particular phase. So, in order to do that, we have to draw free energy composition diagram along with the plot of ΔHmix as well as plot of minus ΔHmix. So, that means ΔGmix would have effect from both ΔHmix as well as minus ΔHmix. Since this is slightly positive, I can write it like this, and that time we are considering this is constant at temperature T, where we are considering this particular plot. This is ΔHmix, and minus ΔHmix will be always negative. So, minus ΔHmix. So, ΔGmix would be in between So, this would be my ΔGmix, and here G and this is XB. So, this is a situation because this is a combination of both. So, that is what we are getting in between, but this situation would be different if in the center position this value is greater than this value, if we take the mod value of both the cases, and that time situation would be little different and we will get entirely different plots. So, we will discuss it in our next lecture. Thank you.